Hi, everybody. Okay, let's look at one more example of finding an extreme point um, in an interesting case where you are asked to find the closest point on the plane x minus y plus z equals 4 to the point 1, 2, 3. Oops, 1, 2, 3. Okay. So we're asked to find the point on the plane that's closest to this point. So how are we going to do that? Well, to find the closest plane, the closest point on the plane to this point, what we want to do is minimize the distance from the plane to that point. So in other words, if you're sitting in 3 space and you have a plane somewhere, I'm not sure that this is that plane, but to make the idea, and then we have a point away from the plane, so here's point P, then what you want to do to find the nearest point is you want to look at the distance to a point in the plane and then find the minimum of that distance. So you want to find the minimum of the distance from the point, let's call our point P, to the plane. Um, let's say from distance from vector x to the point P. So we'll call this our point P. Okay. And vector, where vector x equals xyz is in the plane. Okay, so we can rewrite our equation for the plane as 4 minus x plus y. Okay, and what's the distance formula for a point to the plane, to a plane? Well, if xyz lies on the plane, then the distance from xyz to this point P, which is the point 1, 2, 3, is going to be the square root of x minus 1 squared plus y minus 2 squared plus z minus 3 squared. Okay, and so that's the distance from any point xyz to from any point xyz in the plane to the point P. Okay, and so if z is in the plane, I can rewrite that. Actually, this one's the distance of any point xyz to the point 1, 2, 3. But if z is in the plane, I can replace z by this equation and get a function of x and y. So I have 4 minus x minus y minus 3, quantity squared. And so d is the square root of x minus 1 squared plus y minus 2 squared plus 1 minus x minus y, quantity squared. Okay? And now you notice you want to minimize this. But if I minimize the distance, since that's a positive number, it's just as well to minimize the distance squared. And then we don't have to worry about square roots. Okay? So if we minimize d squared, we're just as good because whatever point works for that also minimizes d. All right, and so now we have just a straight function. You could think of this as a new function. If you like, give it a different name. If writing d squared makes you uncomfortable, call it capital D. And now we want to find a minimum value for capital D. So how do we do that? Well, we know we learned how to do that already. We find the critical points. So I take f sub x, which will be 2 times x minus 1 times 1 plus 2 times 1 minus x minus y. Sorry, I think this should have been an x plus y. I copied this wrong. This should be a plus. Okay, that's important. You have to copy things correctly. That's really important. Okay, so this is 1 minus x plus y to the first power times the derivative of what's inside with respect to x. So that's a minus 1. And so let's simplify that a bit. So that gives me 2x minus 2 plus 2, minus, because we have a minus there, minus 2 plus 2x and minus 2y. And so that gives me 4x plus 4y, 4x plus, my goodness, can't talk, 4x minus 4 minus 2y. There we go. That's f sub x. Okay. And now we do f sub y. So f sub y is 2 times y minus 2 to the first plus 2 times 1 minus x plus y to the first times 1, because the derivative of what's inside with respect to y is just 1. So that is 2y minus 2 plus 2 minus 2x plus 2y. So this one becomes 4y minus 4x, minus 2x. And then there's no constant because the constants cancel. Okay. All right. All right. So now we have to set each one of those equal to 0. Okay. So we set 4x minus 4 minus 2y equals 0. So that says 4x minus 2y equals 4, which I could divide by 2 and make that a little bit nicer. So I'll get 2x minus y equals 2. So that's one constraint for a critical point. And the other constraint is that f sub y is 0. So that says 4y equals 2x, which says that x is equal to 2y. Okay, and so now if we plug that into here, x is equal to 2y. So this becomes 4 times 2. So that becomes a 4y. So using this one, 4y minus y equals 2. So that says 3y equals 2, or y is 2/3. And so x is 4/3. Okay. Okay. All right. So now we have our critical point. And let's check that that's a minimum. So that says our point is 4/3, 2/3, and then the z value, the point that we have as a candidate for being the closest point, is z is, remember, 4 minus x plus y. So that in this case, so z at x equal 4/3, y equal 2/3 will be 4 minus 4/3 plus 2/3. So that's 4 minus 2/3. So that is 6. That is 24/3 minus 2/3 is 22/3. Okay, so this would be 22/3. Okay, now is it a minimum? Just because you found it doesn't mean it is. You have to check that. Okay, so how do you check that? You check the second derivative. We have a critical point, and now we look at maybe capital D wasn't the best letter because we use that in the book, in our book for this. This is fxx fyy minus fxy squared. Okay, so we need second derivatives. So let's go back and refer to what our f sub x and f sub y were. So here's my f sub x. So f sub xx is going to be 4. f sub y, if you remember, here's our best form for f sub y. F sub y is going to be 4. And fxy, or you could just as well do fyx, but fxy is going to be minus 2. And so now when you look at this at the point, let's call this one P star. So D evaluated at the point P star, then is going to be 4 times 4 is 16 minus 2 squared. And so our second derivative check term is positive. And now when you look at fxx at P star, that is positive. Therefore, our point 4/3, 2/3, 22/3 is a minimum, is a relative minimum, okay? And since it's the only minimum we found, and we're looking for a point to the plane, you know there has to exist a minimum, that's it. Whoops, okay, so sorry, I ended up writing off the screen. But fxx is 4, fyy is 4, fxy is minus 2. So when you compute this for those values, you get a positive number. That's all you care about. You don't care about the exact number. And remember, you have to check the sign of the second derivative with respect to x at the point you're interested at the critical point. And at this critical point, fxx is positive. In fact, at any critical point, fxx would be positive because it's always 4. So if d is positive and the second derivative with respect to x at the critical point is positive, then you're at a minimum. Okay, so that's another example of how you find a minimum distance from a point to a plane.